The following problem tells us that the total yearly profit to a car dealer from selling X cars per year is given by P of X is equal to negative 8x cubed plus 140x squared plus 80x. We need to find the total number of cars sold that will maximize the dealer's average profit rounded to the nearest car. So we're maximizing the dealer's average profit is the key word here. Because we're maximizing the average and P of X represents the total profit, in order to get the average profit, which we denote by P bar of X, then we need to take our total profit P of X and divide that by the number of cars sold, which is X. When we do that, we'll get negative 8x cubed plus 140x squared plus 80x, all divided by x. And when we have this, we're just going to factor out an x from the numerator. All of our terms have an x in common. So we'll get x times negative 8x squared plus 140x plus 80 all over x. And now we have a common x in the numerator and denominator that we can cancel out, leaving us with P bar of x is equal to negative 8x squared plus 140x plus 80. This is what we are maximizing. We're not maximizing P of x, but we're maximizing P bar of x, the average profit. So in order to maximize it, or in this case just find the number of cars that maximizes it, we're going to take P bar and find its first and second derivative. So P bar prime of x is equal to the derivative of negative 8x squared plus 140x plus 80. The derivative of negative 8x squared, remember you're going to multiply the exponent out front and then subtract 1 from it. That gives us negative 16x. Then the derivative of 140x is the same thing. You'll multiply the exponent out front. In this case, the exponent is just 1. And then subtract 1 from it as well, which just leaves us with 140 times x to the 0 power. But x to the 0 power is just 1. So it just goes away, leaving us with the 140. And then finally, the derivative of any constant, in this case 80, is just 0. So our first derivative is negative 16x plus 140. Now we can find our second derivative. So the derivative of negative 16x, just like the derivative of 140x, is just going to be the number that's multiplied to our x, which in this case is negative 16. So we get negative 16, and then the derivative of 140, just like the derivative of 80, is 0. Okay, so we're performing the second derivative test right now in order to maximize this function. And the way that you perform the second derivative test is you take your first derivative, the negative 16x plus 140, and you set that equal to 0. And that allows you to solve for x, giving you your partition numbers. So we'll add 16x to each side, giving us 140 equals 16x. And then if we divide each side by 16, we'll get x equals 8.75. Now that we have this number, we need to plug it back in to the function that we took our first derivative of. So we need to plug it back into p bar of x. So in this case, we'll replace our x with 8.75. And when we're plugging this in, we're doing this because we need to make sure that the result is a real number. We don't actually care what the result is because we were never told to maximize the average profit. If we did want to maximize the average profit, this is what would do it. But all we care about is just deciding if this is a real answer, meaning we can't get an imaginary number or division by 0 or anything like that. And when you evaluate this, you end up getting 692.5. And that is a real answer. It's not imaginary, it doesn't have division by 0, which tells us that x equals 8.75 is a critical number. So because this is a critical number, that means that at this location, there will be a maximum or minimum, or possibly neither, but it gives us a testing location at least. So this is when the second derivative comes in. Remember, we call it the second derivative test because once we find our critical numbers, we test them in the second derivative. When we plug 8.75 into the second derivative, there's nothing to plug it into, so the result will always be this negative 16. If we said x equals 1,000,000, p bar double prime will still be negative 16. And remember, your second derivative tells you concavity. So if your second derivative is positive, then your graph is concave up there. If it's negative, it's concave down. In this case, because it's a negative 16, then that means it's concave down, which means that we have a maximum. So we have just proved that at x equals 8.75, we have a critical number, and that critical number represents a maximum. So we were asked to find the number of cars that will maximize the average profit, rounded to the nearest car. So we'll say selling, and it's probably better if I just type this, selling 9 cars will maximize the dealer's average profit per car. And that is our solution.